Okay, thank you. And thank you also for your contributions to this work. So I'm Chris Kiekintveld. This is joint work with one of my students at UTEP, Anjon, Basak, Fang, and also Thanh, Nguyen. All right. So how do I move to the next slide? Page down? No. Okay, there we go. Okay, so I'm going to skip pretty quickly through a lot of the motivation because actually this is very closely related to the previous talk. We're also thinking about these kinds of environmental crime situations where we may need to do patrolling of forests or water areas or other sorts of large spaces. I think most of us are familiar with the common kinds of challenges. We're trying to do patrolling and detection in these very large, potentially very remote regions using very limited resources. So we want to be able to somehow come up with better ways of optimizing the use of the resources that we have. So the framework that we're thinking about here is actually more in the strategic space. So we're thinking about game theoretic kinds of models, which are really in the extreme end of fully strategic models. But I think the basic ideas that we're exploring here computationally could also potentially be applied to the more dynamic learning-oriented models. So basic security game model, which we're going to use here, has two players, an attacker and a defender. Think of them as a poacher and a set of forest rangers. They're interacting in some physical space that we are going to model using a graph. The challenge for the defenders is coming up with optimal patrolling routes. They're going to be randomizing potentially over multiple routes so that they're unpredictable. The attackers or the poachers are picking places to conduct attacks or, in this case, poaching activities. And the utilities in the game are going to be basically zero sum, and they depend on the animal density. So poachers want to go to areas with high animal density, and we also want to protect those areas. Okay, and we're actually thinking primarily about the scheduling constraints and the routing problems in these kinds of networks. So we actually do want to have routes that make sense in the forest, where you actually have to obey the terrain constraints. And often we can capture that using a sort of graph model. So if this is a physical space, in this case it's a density map of elephant densities in a national park in Uganda. We can translate that into a graph that looks something like this, and we're interested in finding these paths through the graph. So if we're thinking about a game theoretic model, a standard way of calculating a solution for those security game models is using something that we call a Stackelberg Equilibrium, where we are trying to find the optimal strategy for the defender, assuming that the adversary is going to observe a strategy and choose a best response. And we have standard linear programming formulations. I'm not going to go into the details of that, but normally we think of linear programming as very efficient. But the problem here is that as we increase the size of the graph, the number of variables in our linear program increases exponentially. So even these linear programming approaches fail quite quickly. They run out of memory, run out of solution time as you increase the size of the problem. So the big idea that we want to look at here is how can we use automated abstraction techniques to simplify the problems and increase the scalability by orders of magnitude that we can get in these kinds of games. And these kinds of techniques have been quite popular recently in the computational game theory community, looking at things like computer poker, but there's been a very limited attention to them in the context of security games, so we're trying to bridge that gap here. So the basic idea of how a game abstraction works, if we have the original game in great detail, it's going to be very, very large. We want to come up with automated ways of calculating an abstracted or simplified game. We're going to apply our solution concept, in this case finding an equilibrium strategy of that game. And then we're going to map that back into the original game using a reverse mapping so that we can actually play the strategy in the original game. Okay. So this is a terrain map that Fang gave us from one of the original PAWS applications. So if you can kind of see the size of the pixels here, each of those pixels represents a 1 kilometer by 1 kilometer square area. So this is actually a very large area. And the point is that the original data here is that level of granularity, if we try to construct a graph and apply one of our solution algorithms, existing solution techniques for calculating equilibrium, it fails completely for this kind of graph because you simply run out of memory. So they've done actually a lot of very clever things in the pause applications to be able to solve these games. And a lot of that has involved doing some sort of manual abstraction, thinking about how to come up with a variation of these games that you can actually feed into a solver. So our goal here is actually to automate that process so that we don't have to have manual sort of ad hoc kinds of abstractions going on, and we can actually operate on the original data. And to do that, we've started to apply some ideas from the graph theory literature, where they've been looking at these kinds of problems for a long time, particularly in the context of pathfinding. So these optimal patrolling problems are very closely related to pathfinding problems on graphs. And there are contraction methods that have been designed for pathfinding. The basic idea is that you want to remove nodes from the graphs. You identify nodes to remove from the graphs using typically some sort of heuristic strategy. You remove the nodes and you consider adding supplementary edges to your graph in place of this node. And you do some sort of pruning to identify unnecessary edges. So we think that this kind of technique is very promising for green security games in particular due to the characteristics of the problem. So if we go back to this animal density map, we notice that there's a relatively small number of areas that have very high densities. And many of the other areas are either inaccessible or just areas where there's very little animal activity. So in the game theoretic context, this translates to a problem where we have relatively few important targets that may need to be connected by traversing these relatively less important areas. Okay? So this naturally leads to some kinds of abstraction ideas where we're going to keep around the important targets and try to abstract away the detail from all these unimportant areas. Okay? So I'm going to not go into great detail in the algorithm, but our basic idea, we're going to select some nodes that we're going to remove from the graphs using some heuristics based on the target values and the distances that you need to travel. We remove those nodes using a contraction procedure that I'll show you on a graph here. So if we have this kind of graph and we wanted to remove this node 3, we would first generate supplementary edges and say, well, there's a path potentially from node 3 to 7 that would have gone through node 3 that has a length of 20. But in fact, in this graph, that can't be the shortest path because we already have another path that's still in the graph of length 10. So we can prune out those kinds of unnecessary edges, resulting in that kind of graph. If we tried to remove after that the node 4, we would generate these potential edges. Some of them are unnecessary, but some of them, in fact, could be the shortest path between other nodes that are still in the graph. So we would need to keep those nodes in our graph. And if we do this for a number of nodes in the graph, we end up with something like this, which has far fewer nodes and fewer edges, but many supplementary edges have been added to retain the shortest paths. Okay. So that gives us a procedure. We can take the original graph of the terrain. We can apply our graph contraction methods to come up with a much simpler graph, which translates to a simpler game representation, which we can then solve using existing algorithms, either to find exact or approximate equilibria, and then we can translate that back into patrolling routes that we can actually execute in the original game. So we've run some experiments on simple graphs to try to understand what is the potential improvement that we can get by using these sorts of abstraction techniques. And I've got just 2 slides to demonstrate this. So we have runtimes here on the y-axis, and we're increasing the amount of contraction that we do. So we're removing more and more nodes. These lines along the bottom are the time that we actually need to calculate the simplified graph. And this is the solution time. So this is exactly what we would hope to see, is that we're getting dramatic reductions in our solution times. And if we compare that to the amount of error that we are introducing in our solution concepts, both of these are on a percentage basis. So the large bars are the percentage of your solution time that your increases very quickly up to almost 100%. So we're getting dramatic reductions in solution time. The small bars, fortunately, are the amount of error that we introduce relative to the optimal solution. So for very small percentages of error, we're getting dramatic increases in our solution time. And so these are actually somewhat dated results. We've been working on actually integrating these with more sophisticated solution techniques. And we're now able to solve problems that we could not solve at all due to memory constraints before in just a matter of seconds using the most advanced algorithms that we have. Okay. So these kind of graph-based security games can be used across many different kinds of domains, including anti-poaching and so forth. They still pose great computational challenges, but I think we have some really interesting directions to attack those problems using these kinds of automated abstraction techniques. And we're thinking now about how to look at computing not just equilibria, but also concepts that account for uncertainty and dynamic interactions with defenders like the previous talk. This is also interesting because it allows us to draw on a lot of the related work that's been done previously in domains like pathfinding, which are closely related to the green security games. So thank you very much.
So you're referring to having to repeatedly solve linear programs, but I would imagine these would be integer programs, right? I mean, aren't you having to, or do you have mixed strategies here?
We do have mixed strategies here for the defenders. So the defenders are playing a distribution over potential patrolling routes. Okay. So you're randomizing which route you're taking so that they're unpredictable.
So it's Stackelberg.
Yes.
But it's repeated Stackelberg, so then it's essentially...
So the solution concept here is just a one-shot game. So it's a one-shot Stackelberg game where the defender chooses their randomized patrolling strategy, and then the attacker best responds. Yes. Although I think that, as I said, so the kind of abstraction technique is almost independent of the solution technique. So you could do this kind of abstraction and then do some sort of other solution technique. Yeah.
I have a naive question. If you look at your original large graph to start with, the transitions which are in it, they represent a very specific set of directions of motion, and they already restrict sort of the possible types of routes you could have in there. So it seems, given that you're pruning it after that, it seems almost like there is a number of important implications, and then you want to solve a continuous problem of finding the quickest paths in the jungle from the point A to location B. Doesn't this procedure indicate that building that original graph of its connectivity is problematic? Wouldn't it be better to identify the nodes you want to retain, abstract away the original graph, and then solve the continuous problems for the quickest paths?
So I mean, that's actually very close to the idea of what we're doing here, except for the continuous parts. So we're using the graph-based abstraction, so it's all discrete. I haven't thought about solving it as that part of it as a continuous problem, but it seems like it would work potentially. Yeah, I'd have to think about that a bit more.
All right, let's set the